We've been looking at electrolytes and how they form ions when put into solution, and we call it dissociation. But even if we have pure water, there's small amounts of some ions that have been formed by the water. We're going to examine this, and we're also going to look and see how does adding electrolytes to water affect the concentration of these ions. Water dissociates a teeny tiny bit in this equilibrium shown here on the second line. A water will break apart and make a proton, H+, and hydroxide, OH-, and then they'll rejoin again and make a water molecule. You notice there are two arrows written, so it is an equilibrium. This is ongoing all the time in all water, liquid water. Now, this isn't really what's happening, because a naked proton in water does not exist. What happens is that the proton never really forms. It actually jumps onto another water molecule. So the second equation shown, where it's two waters make a hydronium ion, H3O+, plus hydroxide, OH-, is really what's happening, because one water molecule will pull a proton off the other to make the hydronium ion and leave a hydroxide behind. However, this is a much more complicated equation, and it's much simpler to look at the first one to understand what's going in water. So I'm going to be using that equation to explain what we call the autoionization of water. Now, when water is pure and at 25 degrees Celsius, there is a concentration of protons of 1 × 10⁻⁷ moles per liter. And this is steady state, this equilibrium. They're constantly rejoining, the two ions are constantly rejoining and forming water, and water is constantly splitting apart and forming the two ions. But there is a steady state concentration of protons of 1 × 10⁻⁷. Because one hydroxide is made for every one proton that is formed, the concentration of hydroxide is also 1 × 10⁻⁷ molar. The concentrations of protons and hydroxide are the same in pure water, and so it is neutral. It is neither an acid nor a base, because the concentrations of those two are the same.
I want to emphasize that I tend to write protons most of the time, and many texts use this hydronium ion instead of protons. But just realize that a hydronium ion is just a proton attached to a water molecule, and anytime the text or I say hydronium ion, it's the same thing as a proton. Anytime I say proton, it means exactly the same thing as a hydronium ion. Proton concentration is important. If you change your proton concentration, you can really upset the balance of what's going on in biological systems. Raising or lowering proton concentration will kill a lot of organisms. If I look at where is proton concentration important, it's important in soils, it's important in the cells of plants, it's important in the bloodstream of human beings, it's important in a lot of places, and these slight variations that we have can greatly change what's going on in biological systems. So we're going to look at proton concentration so you understand it better. Proton concentration is measured quite easily. We have probes we can stick into the soil, probes that we can stick into solution, and immediately report what is our proton concentration. Now, we have a shorthand for writing concentration in molarity, and that is to put brackets around what we're talking about the concentration of. So when I have bracket, proton, bracket, that means the concentration of protons in molarity. If I have bracket, hydroxide, bracket, that means the concentration of hydroxide in molarity. At 25 degrees Celsius, I find that pure water has a proton concentration equal to a hydroxide concentration that is 1 times 10 to the minus 7. Now, equilibria, we didn't really go in real deep in equilibria, but in equilibria we can multiply the concentration of components of an equilibrium and it gives us a constant, meaning that doesn't change. So in this equilibrium we can multiply proton concentration times hydroxide concentration to give us 1 times 10 to the minus 14, and that equation always holds in water. Of course, this is at 25 degrees Celsius. We call this constant 1 times 10 to the minus 14 kW, or the equilibrium constant for water. That is 1 times 10 to the minus 14 is equal to proton concentration times hydroxide concentration all the time. This always holds. That means that when proton concentration is increased because you add an acid to something, then hydroxide concentration must decrease. Or if I add hydroxide concentration to something, well then proton concentration has to go down. These things are mathematically tied together, and we find they behave quite regularly in nature, and we can predict things that are going to happen. So I can use this in problems to try to understand what's going on. If I look at this problem, I'm giving you a 0.025 molar solution of nitric acid, and it's saying determine the proton concentration and the hydroxide concentration of this solution. I can figure out what are those concentrations by knowing what does nitric acid do in water, and by understanding that proton concentration times hydroxide concentration is equal to 10 to the minus 14. So nitric acid is a strong acid, and so when it's put in water it makes protons and nitrate. No nitric acid remains intact, nitric acid remains behind. So if it's 0.025 molar nitric acid, that means I have 0.025 molar of protons. That also means that I have 0.025 molar of nitrate. Now we're not going to worry about the nitrate. It has no impact on our hydronium ion concentration. Only the proton concentration will impact the hydroxide ion concentration. Let's go ahead and look at the equation now, and that is that proton concentration times hydroxide concentration is equal to 1 times 10 to the minus 14. I can rearrange this equation. I know what my proton concentration is, and I want to find out what my hydroxide concentration is. So I rearrange this equation by dividing both sides of the equation by. That gives me that hydroxide is equal to 1 times 10 to the minus 14 divided by proton concentration. I can then put in what I know is proton concentration, 0.025, and put in my calculator 1 EE negative 14 divided by 0.025, and I will get 4 times 10 to the minus 13. So that means when I have a 0.025 molar solution of nitric acid, I know what my proton concentration is, 0.025 molar, and I know what my hydroxide ion concentration is, 4 times 10 to the minus 13 molar. So now what I'd like you to do is stop and try this problem, and when you get through, check your answer. To determine the proton concentration, the hydroxide concentration, the first thing I need to do is write the reaction that's occurring in solution. Calcium hydroxide will dissociate to make a calcium 2+ ion and 2 hydroxides. That means that if I have 0.00010 molar of calcium, then I have 0.00010 molar of calcium ions, and 0.0002 molar of hydroxide. The calcium ion concentration is not important to this problem. What we need to focus on is the hydroxide ion concentration. Proton concentration can be determined from hydroxide concentration because this equation, protons times hydroxide equals 1 times 10 to the minus 14, always holds. So I can rearrange this to solve for proton concentration. Proton concentration is then equal to 1 times 10 to the minus 14 over hydroxide. I can then plug in my value of hydroxide concentration, and I can get that my proton concentration is 5 times 10 to the minus 11.